Hello everyone, Mr. Fawcett here, and I'm going to be bringing you another lesson about derivatives. Today our focus is going to be on graph representations for the most part. So looking at the graph of an original function and thinking about what the derivative may look like, and we may even be sketching some graphs ourselves based on some initial conditions that were given about either the original function or the derivative. So let's start off. Let's do a quick I guess it's a one-sentence review from yesterday, or the last video. It says, we have previously discussed how a derivative is the blank of a tangent line to the function at any given point. So another name for derivative is slope of a tangent line. It says complete the table below by drawing tangent lines at the different points and estimating the value of each derivative. Then use it to write the equation of a tangent line at the given point. We're going to skip the step of writing the equation of the tangent line. I don't think that needs to be our focus here for understanding what's going on at the function given what the derivative looks like. So what I do need you to do before we review this together is you're going to go through this chart and you see you have a bunch of these x values, and you're just going to estimate the value of the derivative for that given x value. So I gave you one example, and if we just go through what that's saying, so at x equals -7, and again the axes aren't labeled, but they're marked off by units. So -1, -2, -3, -4, -5, -6, -7 would be right here. So our tangent line would look something like that. And they're estimating that to have a slope of +4. Now, you don't have to come up with the exact slope, but you should never say that that slope is 0 or negative because it's clearly positive. So just estimate it. You don't have to, pick 2 points and come up with the change in y over change in x. Just estimate what you think the slope is, but at the very least, you should get it right whether it's positive, negative, or 0. Once you come up with that slope, or an estimate, you're then going to look at the function and think about what it's doing at that point. So at this point, x equals -7, is the function increasing, right? Or decreasing, or maybe it's doing neither. Maybe it's in between increasing and decreasing at that specific x value. So you're also going to answer that question as well. And then you're going to take a look at the relationships. So maybe you look at every spot the function's decreasing, and maybe the derivatives are all similar there. Or maybe at every spot the function's decreasing, the derivatives are all similar. So fill in the chart, see if some patterns stand out to you, and then we'll talk about some of these relationships. Okay, so hopefully you've had a time to fill in the chart. I'm just going to go through a couple of these with you, just the ones that fit on the page. So we already did x equals -7. Let's do x equals -6. So we have a tangent line that looks something like that. I'm going to say that it has a slope of about 3, and the function is still increasing at that point x equals -6. Let's do the next one. We have x equals -4. And our tangent line here, it's right at the top of this section of the graph. So if you think back to the slope of a horizontal line, it's going to be 0. And right here, the function is between increasing and decreasing, right? It's coming up, but then on the other side, it's going down. So at this apex, it's actually doing neither, but we would call this a relative maximum. Okay, so if it's not increasing or decreasing, it could have a relative max or a relative min. Let's look at the next x value. We've got x equals -2. Got a tangent line that should look something like that. And again, we're just estimating. I'm going to say that it has a slope of about -1. As long as you have the slope that's negative, that's going to be okay. And here the function is decreasing. And we'll do one more at x equals, the next one is at x equals 1 rather. Okay, and we have, again, we have this slope of 0. This time it's not a relative maximum though, because the function's coming down and then going up. So this would be a relative min. Relative minimum. And you could fill in the rest of the chart. We're not going to, just because I want to be able to see the graph in the chart here. But let's think about what some patterns, what are some patterns that we see here. So if you haven't already, take a minute or two, think about some patterns, and then maybe you could write down some relationships, because on at the very top of the next page, there's 4 key things we can pull out of this chart and graph combo. Okay, so we'll talk about these things. Actually, you know what? Yeah, we'll talk about these things and we'll write them down on the next page. So if you look at your chart, you should have several spots where the derivative is positive, right? The only spot we have right here is at x equals -6, but down below you should see at least one more. And the function was increasing. So one relationship between derivatives and the original function is if the derivative is positive, the function's going to be increasing at that spot. And even though we can't see the rest of the chart, we could draw some other tangent lines, right? So here at this point, oops, let's draw that a little better. At x equals -7, the derivative's positive. At x equals -6, the derivative is positive. At x equals 3, the derivative is also positive. So we have 3 points on this graph where the slope of the tangent line, i.e. the derivative, is positive, right? The tangent line has a positive slope. And at each of these points, the graph is increasing. So whenever your derivative is positive, the original function is going to be increasing at that x value. Okay, let's see if the opposite holds true for decreasing. So let's look at all the points on our graph where the tangent line has a negative slope. So we've got this point right here, x equals -2. We've got x equals -1. Wasn't the best tangent line, but you get the idea. And we have this point right here. This looks like it's x equals 7. So here we have 3 spots on our graph where the slope of the tangent line is going to be negative. And if we look at the graph at all 3 of these points in orange, the graph is decreasing. So that's our second relationship. If the derivative is negative, then the original function is going to be decreasing at that point. The other option we had, right, was when the derivative was neither positive or negative. So our first example was when the derivative was 0, but we had a relative max. So think about how you could know when the function had a relative max, because we can't just say when the derivative equals 0, because in red, the function had a relative max when the derivative was equal to 0. But down here in blue, the function had a relative minimum when the derivative equals 0. So think about, there's some other piece we have to put in there to determine whether the function is going to have a relative min or relative max when the derivative equals 0. Okay, so to determine whether when the function has a relative max, the first thing is the derivative has to be, well, it doesn't have to be 0. We'll look at some other cases where it could be undefined. But in this case, it's going to be equal to 0. And the function has to go from increasing to decreasing. Okay, so, and you could think about this intuitively. If the function is going up and then coming down, you're going to have a maximum point up there. Likewise, if the derivative is equal to 0 and the function is going from decreasing to increasing, right? If you go down and then you come back up, well, that point at the very bottom is going to be the lowest point. It's going to be a relative minimum. So those are the 4 relationships we can pull out of this graph and table. I am going to go to the next page, and I'm going to put those 4 relationships on the page just so we have them in Word form, and then you can feel free to copy them down. All right, so here are the 4 relationships that we need to be taken away. Again, just to reiterate these, if the derivative, so if f prime of x is less than 0, then f of x is going to be decreasing. If f prime of x is greater than 0, then f of x is increasing. Number 3 and 4 deal with the relative min and the relative max scenarios. So if f prime of x, if the derivative is equal to 0, and f prime is going from positive to negative. Now, if f prime is going from positive to negative, f of x goes from increasing to decreasing, right? Which means we're doing something like this with our graph. Then we're going to have a relative max. But if the opposite is true, if f prime of x equals 0 and f prime of x is going from negative to positive, which means the original function goes from decreasing to increasing, then f of x has a relative min. So if our function comes down and then goes back up, right, that point at the bottom is going to be a relative minimum. So these relationships are nice because if you don't have a graph, so maybe you have a table or just an algebraic form of the function, you can figure out what's going on with the graph based on what's going on with the derivative. So if it's a complicated function that you don't know how to graph, you can still have characteristics of the graph become apparent based on what the derivative is telling you. Before we end this video, let's do a quick example where we have a table and we're being asked to state different characteristics of the function at 4 different x values. So take maybe 4 or 5 minutes, fill in the table, and again, you're going to be estimating the derivative. So the way we do that with a table is we take the points on either side of the given x value and just perform the slope formula. So essentially what we're doing is we're taking these 2 points on either side of our x value, right? So if our x value is 0, we're going to take the point directly to the left and directly to the right, and just find the slope of the secant line between those 2 points. Remember, we did this demo where we looked at how the secant line can approximate the tangent line, and the closer the points are to where the tangent line would be, the better the approximation of the secant line is going to be in general. So again, we'll just do change in y over change in x, which is y2 minus y1 over the quantity x2 minus x1. So I'm going to have negative 3 minus 2 divided by the quantity 1 minus negative 3, and that's going to give me negative 5 over positive 4. So my slope, the estimate for my slope when x equals 0 is negative 5/4. And then we're being asked, is the function increasing, decreasing, or does it have a relative maximum or minimum at x equals 0? Well, if our best estimate for the slope at x equals 0 is negative, then we would state that the function is decreasing at that point. Okay, so that's what you're going to do to fill in the last 3 rows of this table. And again, this process right here is how you estimate the derivative or the slope of the tangent line at a specific x value. You just take the point on the left, take the point on the right, and you find the slope of what that secant line would be. Okay, so hopefully you've had time to finish the rest of the chart. We will do one more example together, and then I'll just give you the derivatives for the last 2. If I am looking for the derivative at x equals 1, well, I'm going to take the 2 points on the other sides. So at x equals 0 and x equals 4. And it is true, some of these points they seem far away, right? 4 seems pretty far away from 1 to give us a great estimate, but it's the closest point we're given, so it's a point we have to work with, right? If they gave us the point at x equals 1.1, then we would certainly use that point instead of x equals 4. But if x equals 4 is the closest point on the right-hand side to 1, then that's the one we're going to go with. So here we have change in y over change in x, and we're going to do 0 minus 1 from my y2 minus y1, and we're going to do 4 minus 0 from my x2 minus x1. This is going to give me negative 1 over 4. Again, negative slope, so it means our function is decreasing. You know, we will just quickly go through the last 2 here. At x equals 4, the 2 points to either side are right here. So change in y over change in x, it's going to give me negative 7 minus negative 3 divided by the quantity 6 minus 1. So that gives me negative 4 over 5, which is also negative, which means the function is decreasing. Let's see if our last point gives us something different. So our last point is that x equals 6, which means we're going to be looking at these 2 points right here. So change in y over change in x, it's going to give us 2 minus 0 divided by the quantity 10 minus 4. That's going to give me 2 over 6. You could leave it as 2/6 because it means the same thing as 1/3. And on a calculus, certainly on the AP exam, if it's an open-ended question, you do not have to simplify unless they specifically say so, and most of the time they won't. So this just saves you from making a mistake when you simplify, right? If I had simplified 2/6 to 1/4, then I'm not going to get credit. Whereas if I had left it as 2/6, I would have. So if our derivative is positive, that's going to mean our function is increasing. So we didn't have a chance to talk about maximums or relative maximums or relative minimums here. But when we come back for part 2, we're just going to be working on several different types of practice problems where, again, all 4 of these relationships are going to come into play. So until then, this is Mr. Fawcett. Enjoy the rest of your day.